All right, so here we're looking at 4.5 exponential growth and decay and modeling data. So we're looking at exponential growth and decay models. First thing we're looking at. So notice it has our function is f of t is equal to a naught. We have this a sub zero down here, this a naught, e to the k times t, or f of t can be substituted by just the letter a. So we have a equal to a naught times e to the k times t. Don't forget e is our exponential function. All right. So if k is greater than 0, so in other words, if k is positive, the function models the amount or size of a growing entity. So if k is positive, it models growing or growth, exponential growth. If k is negative, or in other words, if k is equal less than 0, the function models the amount or size of a decaying entity. In other words, models decay, some decay model. Meant to make sure we're okay. You know, your exponential growth graph goes up like that. Then decay, though, will go down. So it either grows exponentially or decays exponentially. Just rough sketches, you know. I can go faster. Okay. All right. So these letters, we have a naught is the original amount or size of the growth or decay, growing or decaying entity at time equal to 0. So really could have said t equal to time, but that's, you know, I'm gonna throw it up there in a second. A is the amount at time t. So after a certain amount of years have passed, or a certain amount of hours have passed, or whatever the time measurement is at that moment, A is going to be how much there would be after a certain amount of time has passed. K is your constant, representing the decay or growth rate. Then, like I mentioned, T is equal to time. All right, so what I did was there are only like 7 problems in my math lab, so I did about 5 of them. One of them is a definition one, which I already gave you the definition of it actually, and then the 7th one, you know, you can work it out, give you an opportunity to apply what you got here. But majority of the problems you'll see on the screen, and I'll walk through them to show you how to do them. So, looking at this first one, and I just doing something a little different. Not going to do all of them like that. Other ones I just pull random examples, but since this one is dealing with word problems and everything, I just went ahead and walk you through it just like we have it. So here, exponential model, A is equal to 103 e to the 0.03 t. Describes the population A of a country in millions, t years after 2003. And then says use the model to determine the population of the country in 2003. So this model represents t years after 2003, and they want us to use the model to determine the population of the country in 2003. So here's the model that they gave us. You know, we got that from the problem, 103 e to the 0.003 t. Once again, t represents years after 2003. Now we want to know how many millions are in 2003. So if it is 2003 right now, that means no years have passed since 2003. So that means t is going to be equal to 0. So if no years have passed, t is equal to 0. So we plug in 0 for t. 0.003 times 0, e to the 0 power is 1. So anything to the 0 power is 1. So 103 times 1 is 103. So that's how that works. If no years have passed, then it's 0 for t. Plug in 0. That cancels out your e to the whatever. And you're just left with the number that's sitting in front of e, which is 103. So you have 103 million, in 2003. All right, looking at the next one. Complete the table shown to the right, population growth for a certain country. So they give us in 2006, 70.8 million is the population. They want to know what's the projected for 2043. And they give us the growth rate K of 0.0131. So the initial year is 2006. A naught, the initial amount of people in 2006 is 70.8. That's what we got from the chart. Now we're talking about going from 2006 to 2043. So we subtract those values, and that's 37 years. And they gave us K, which is 0.0131. So plug it in accordingly into the formula. A naught, 70.8. E is a part of your formula. K, they gave us 0.013. And then we want to know in 37 years, 2043 is 37 years from 2006. So plug in that 37 per T, and they give us 114.957, and they wanted us around to 1 decimal place. So that's why it ended up being 115.0. Don't forget to make sure you know how to use your calculator. If you have any questions about using your calculator, make sure you get with me. But I just threw that in the calculator. All right. Next one. Complete the table. And they give us population in 2004 is 39.7. Projected population for 2036 is 20.8. And then they want us to find K, the projected growth rate. All right. So we always extract from the problem what we do know. So the initial amount is 39.7. Now we're going from 2004, excuse me, to 2036. So we subtract those values, we get 32 years. And 20.8 is what it goes to. So in 2036, the population will be 20.8. So plug in the values of what you do know into your growth decay formula. Only one that should be missing is K, because that's what we're looking for. So 20.8 goes in for A, future value, or projected value. 39.7 is our initial value. And then 32 is the years past. So we start off solving by dividing both sides by 39.7. They cancel on the right here. And it gives us this result, 20.8 divided by 39.7. Now I need to get E off of 32K so I can have access to that K. So I apply the natural log to both sides. It cancels out over here on the right. So now I have the natural log of 20.8 divided by 39.7 equal to 32K. Then divide by 32. And this is our result. Negative 0.0202 is our K. And then just a note, since K is negative, that means that we have a decay model. Remember, if K is positive, that's growth. If it's negative, that means it's decay or decreases. Growth means it's increasing. Decay means it's decreasing. Remember, our population went from 39.7 down to 20.8. All right, let's look at another one. So we have an artifact originally had 16 grams of carbon-14 present. The decay model is A equal to 16 e to the negative 0.000121 t. Describes the amount of carbon-14 present after t years. Use the model to determine how many grams of carbon-14 will be present in 8,388 years. Once again, start off with what we know. They gave us this formula right here, this model. They gave us T. So we want to know how much will be left after 8,388 years. So all we do is plug in 8388 into T. All right, stuff not erasing. There we go. And throw it in your calculator. Throw this in your calculator. Once again, make sure you know how to use it. You should get 5.799. And excuse me. And they say to round to the nearest whole number. So that's why we have 6 here for our answer. Yep. Any questions? You can get me some water. All right, so question 6, last one. So complete the table to the right for a half-life of a certain radioactive substance. So we have half-life is 15.7 days. And we want to know what's the decay rate. So half-life, the half-life of a substance is the time required for half of a given sample to disintegrate. So that means that projected value is going to be half of what we initially had. So that's A naught over 2. And if you want to figure out the half-life, plug in A naught over 2 in for A. And then notice here, I put a note, we would divide both sides by A naught. And that gives us 1/2 e to the 15.7K. Also, I did mention that 15.7 is our time, so that's 15.7 days. So notice I put that here into the formula as well, still leaning on the same decay growth model formula. We don't know what K is, but we know what time is, what T is, 15.7 days. All right, then we went ahead and put that A naught over 2 in there. So now we want to get access to K. So we take the natural log of both sides. So it's natural log of 1/2 equal to 15.7K. Divide both sides by 15.7. And that'll give us K, our rate, decay rate, 0.044150. All right. So like I said, there were only 7 problems in there. This took us up to problem number 6. So I'll let you have the challenge of attacking problem 7. And let me know if you have any questions. Take care.